Evening class. Today in this for the BSA course, we are going to study the topic of absolute maximum shear force and bending moment in different kind of beams. So let me review what we have already studied in this course. In the previous lecture, or I think in the lectures before, we, for example, I would give you this beam and I would say that give me the maximum bending moment and shear force at this point C due when a set of moving load, let's say this is 1 kilonewton, this is 2 kilonewton. So I would give you this beam and I would ask you to give me the maximum value of bending moment or shear force at any particular point, let's say at this point C. So what was your approach? You would plot the ILD for shear force diagram over this point, and then you will move these place this moving load at different locations over this beam and multiply it with the ordinates, and you will get the maximum value of shear force. Similarly, for the case of bending moment, you will also plot the ILD for bending moment and place the unit loads or moving loads at different location and multiply it with the area, and then you will get the maximum. For the point load, you will multiply with the ordinate, and for UDL, you will multiply with the area, and you will get the maximum bending moment. But let's suppose now you have a simple beam, and the question asks you to give the maximum value of bending moment or shear force over the entire length of the beam. So in this case, you are not given any point, but you have to find a point. For example, previously you were given this point C, and there is a possibility that there is another point B over here at which the bending moment or the maximum value of bending moment exists. So obviously you can calculate the maximum bending moment at C, but it is possible that there is another point existing in the same beam over which the overall maximum function exists. So now our problem is that we will be given or we will be provided with a beam structure or any type of a structure, and we have to find out or figure out the location, or let's say the point at which maximum bending, maximum shear force or bending exists, and also where should we place our moving load to get the maximum value, right? So this is these two things are the main points that we need to compute in this kind of a problem. So let us first start with a cantilever beam. For example, we have this cantilever beam, and the question asks you to compute maximum. Let's say these are our moving load 1, 2, and 3, and there is some distance x1 and x2 between them. And the question asks you to compute maximum shear force in this beam. So can anyone tell me that where will be the maximum shear force in this cantilever beam?
On right side.
On which side?
Right side.
This side. Are you sure?
Yes, sir. Yes, sir.
So you are saying that the maximum shear force is on the right side. Let's suppose I will place my load over here. So the shear force at this point is 0. Yes?
Yes, sir.
So it should be on the left side.
Yes, sir.
So in the case of cantilever beam, wherever I will place my load or external load, the maximum shear force will always be on the left support, or let's say at the point just next to the left support. So now first thing is clear. In case of cantilever beam, wherever I will place my external load, the shear force will be just next to the support. For example, I can place my load over here. Again, the maximum force will be over here. I will place my load over here. The maximum force will be here or anywhere in the beam. Okay. So I have got the point at which maximum shear force exists in the case of cantilever beam. So for this point, I will plot the influence line diagram. Let's say now I have the point, I will plot the influence line diagram for this point, and it will be something like this one. Now this is my influence line diagram. Now I have got the influence line diagram and I know the value of the shear force that I have got for this kind of cantilever beam is the maximum one over the entire length of the beam. And now I will place this set of moving load and I can check the orientation by trial method, and I will place these moving load over this point, and I will get the maximum, multiply with the ordinate, and I will get the maximum value of shear force for this cantilever beam. So for cantilever beam, uh, we have figured out that at what point maximum shear force exists, but this doesn't hold true for all type of beam. Now let's look at.
Excuse me, sir. How much close to the support do we have to place the moving load?
Actually, the idea is that obviously the maximum shear force is exactly at point support. So let's say at infinite, at very small distance next to the support, like a negligible distance, you can say, because there is no shear force or bending moment at the support. It turns out to be zero. So to actually in the physical condition, the maximum shear force is just next to the support. So at negligible distances. So now,
सर ये
if
ILD सर ये ILD एक बार फिर से बता दें जो ऊपर वाली है.
this ILD, so the
Yes
purpose,
sir, yes sir.
so the purpose of this ILD was first I have figured out the point at which maximum shear force exists. So for that
Right.
point, I will plot the influence line diagram for shear force. How will I do that? Again, we cut the beam into two sections, just like this one, and plot the deflected shape. This left part, by the way, this left part won't be moving anywhere. This ILD is not. This left part will remain as it is since there is a fixed support, and this right part will obviously, sorry, I plotted this ILD wrong. So this right part will move up as a whole, and this is my shape of ILD for this shear force. Sorry, this is wrong. Thanks for pointing out. So this is my shape of ILD for shear force, and I will place my moving load at, let's suppose, these points, and I will get the maximum value of shear force for this beam. Okay.
और सर ये जो हम कंसिडर कर रहे हैं ये बिल्कुल सपोर्ट के साथ है कि वो या ये
Yeah,
पॉइंट एग्जैक्टली कहाँ पे?
Exactly at the negligible distance from the support.
Right.
So now it is clear for cantilever beam. Let us do this for simply supported beam. So if we have a simply supported beam, can anyone tell that where will, can you turn off your mic please, someone? So can anyone tell that where will maximum shear force exist for the simply supported beam?
Center of the beam, sir.
Center of the beam. Are you sure? Let's suppose my load is at this point. This is 1, for example, and this distance is 2, and this distance is 4. And what will be this reaction in this case? What will be the reaction?
0.75.
0.75. This will be 0.25. So this is 0.75. It will come over here. This will be 0.25. So maximum shear force is not at the center. It is at somewhere else. So anyone else? Is there any specific point on which the shear force will always be maximum in case of simply supported beam?
Where the load is acting.
Where the load is acting. Let's suppose if there are, what if there are two loads acting?
Sir, I have one question.
Wait a minute. Let's suppose there is another load acting. Then in this case, at this point, the shear force will come down, and again for this load, again the shear force will come down. So this assumption will also not hold true, because in the case of multiple loads, at which load the shear force will be maximum. So again we have to figure that out. So is there any specific point at which the shear force is maximum for this beam? You can think about it. Daniel, yes, you can ask the question.
सर ये हमने ऊपर वाली क्वेश्चन में तो आईएलडी ड्रॉ की है इस ऊपर वाले केस के लिए कैंटिलीवर बीम के ना, और इस केस में हम सिंपल shear force diagram यूज कर रहे हैं.
This simple shear force diagram is just to figure out, because in that case it was easy to tell that where is maximum shear force, and this we will plot the ILD for this beam also, but this is just to figure out for now that where will the maximum shear force will act for simply spotted beam. Just to show you the variation of shear force graph. So can I say that for simply supported beam, the maximum shear force will always be next to or at the support or at one of the support? Maximum shear force is at one of the support. So no matter how much loads are acting on a simply supported beam, you will always get a maximum value of shear force just next to the support. But again, it can be on the right support or it can be on the left support. So for simply supported beam, you will plot the shear force diagram, or simply you will compute the reactions, and from the reaction you can figure out that at which support maximum value of shear force exists. Now you can do the trial and error procedure, and you can see that wherever you will place the point load, you will get the maximum value at either the left support or the right support. So we will, let's say, now we have this beam and we have figured out that my maximum shear force is at left point, and again I will plot the influence line diagram for this left point or for this point. And what will be the diagram? It will be something like this. I have this influence line diagram, and let's say I have these two moving loads of 20 or 10 kilonewton, and again I will place these moving loads over this beam or at somewhere at this point, so I can get the maximum value of shear force. So now two beams are clear. For cantilever, it's also just next to the support, and for simply supported, it is also next to the support, and we have to place the moving load at that point to get the maximum value of shear force. Now let's come back to the cantilever beam. Oh, there is no. Can anyone tell that where will the maximum bending moment exist for this cantilever beam?
The right side.
Right side.
Left side, sir.
Yeah, it should be on the left side. Just plot the bending moment diagram and you can see. And just similar to the shear force diagram, again, at a point just next to the support, we will have the maximum value of bending moment. And again, wherever I place my point load, I will get the maximum value of bending moment at the same point or at the left point for this cantilever beam. Now, where should I place my moving load to get the maximum value of that function, let's say, of bending moment? Now, I have, in the previous cases, I have seen that I place the bending moment at the point where shear force was maximum, let's say at this point. I plotted the ILD and I placed the moving load at the point where the component was maximum, and it was obviously at the same point for which I plotted the ILD. Now let's look at this beam for the bending moment. I will plot the influence line diagram for this point, and the shape would be something. This right part or the left part won't move anywhere, and this right part will be deflecting something like this one. So this is the influence line diagram for, let's say, this point C. Now, in this case, although the bending moment was maximum at this point, but I have to place my moving load, if this is the moving load, so I have to place my moving load at the free end to get the maximum value of bending moment over the entire beam. So there is a small confusion that happens in the case of this cantilever beam when you are going to find the bending moment. So you should look at the influence line diagram to figure out the location of the moving load. You have got the point. It is not same for all the cases that at the same point for which we are getting the maximum movement, we have to place the moving load over that point. We should look at the influence line diagram to figure out that where should we place our moving load to get the maximum value of any function. So is there any confusion about these three beams? If not, then we can move on to the next beam. Now, if we have a simply supported beam, can anyone tell me that where will the maximum bending moment exist in this beam? Or is there any point in simply supported beam that we can say that wherever we place our load, we will get the maximum value of bending moment? Is there any single point?
At center.
At center. Let's say my load is acting at this point. Then what will be the shape of bending moment diagram? It will be something like this one. So it's not at the center. It is at some other point. Anyone else?
एंड्स पे ही होगी फिर जिस तरह ऊपर वाले केस में थी.
But you are looking at this beam. Do you think that it is at the ends? But in the other example, it was at the ends because obviously from shear force diagrams you can see that. But in this case, even in this example, the maximum is not at the end.
हम जहाँ लोड प्लेस करेंगे वहीं पर मैक्सिमम.
Exactly. Actually, the maximum bending moment will be at a point where we place the load. But again, it would be a hectic procedure to place the load at all the points on the beam and calculate the maximum bending moment at those points, and then figure out that at which point the maximum value exists out of all. Let's say I have a 10, I divide the beam into 10 points. I will place the unit load at 10 points separately, and I will get the values of movement, and then I have to select the maximum value of bending moment. But again, this procedure will take a lot of time. So for simply supported beam, we cannot generalize a single point on which maximum bending moment exists. So it depends on the location of the loads absolutely. But again, there is one simple method to figure out the location of moving loads to get the maximum value of bending moment in the case of simply supported beam. Let us look into that. For example, consider that this is my simply supported beam and this is the center line, and I have three moving loads. That is F1, F2, and let's say this is F3. I have been given these distances in the question statement, or I know these distances. Okay. This distance is t1, this distance is t2. The entire length is L, and this length is L by 2. This length is also L by 2. So obviously I know that the bending moment diagram for simply spotted beam under different point load is something like this one. Let's see. And again, these ordinates depend that which load is maximum or at which point the maximum bending moment exists. But this statement is universal that maximum bending moment will exist under one of these point load. But we don't know which point load. One of these point loads. So for now, we will assume that the maximum bending moment is existing under F2.
सर ये बेंडिंग मोमेंट डायग्राम है या आईएलटी?
Bending moment, simple bending moment diagram. So for now, we will assume that the maximum bending moment exists under this force F2. So we have assumed this thing at the start, and we have to figure out that where should I place this load F2 with respect to this center line so that I can get the maximum value of shear force. For example, what I mean is, obviously I can place this set of moving load in different ways. I can place it somewhere over here. But again, if I keep on doing this practice, then there can be infinite number of points. So if I figure out or if I follow some method by which I get this distance, if I call it as x distance, that where should I place my load under which a maximum bending moment exists with respect to the center line, then I will get one clear idea that if I have a set of moving load and maximum bending moment is under one specific point load, then where should I place my unit load, or I should place my unit load at a distance of x from the center line, then I will get the maximum value of bending moment for the case of this simply spotted beam. So let us try to calculate or find out that what should be this distance. If we find the resultant of this force, let's suppose that the resultant of these three forces exists at this point Fr, and the distance of this resultant with respect to F2 is x bar dash. This point is A, this point is D. So now we know this distance as well. If we have been given three loads, let's say F1, F2, F3, and we will be provided with the distances among these loads, and we can calculate the resultant, which is simply the sum of these three forces. And the distance of this resultant we can calculate by taking moment at, let's say, this point M2, and you will take the moment of all these forces and you can calculate this distance of resultant with respect to any force, let's say with respect to F2. So these three things are known to you. And you have to figure out that what should be this x distance, or where should I place my load F2 with respect to the center line to get the maximum value of bending moment. So if I calculate the moment at point B, in class you should be making notes of this. And if I calculate the bending moment at point B, let's say this is A and this direction is AY. So I have one force that is AY into L, and on the other side I have this one force, and the distance is, the total distance from the center line is L by 2. What will be this distance? Can I say that this distance is x bar dash minus x? Okay, and what will be this distance of this resultant force with respect to point B? That will be L by 2 minus x bar dash minus x1. So this is basically the moment arm of this FR force with respect to point B. So if I take the moment at point B and compute the reaction in terms of FR, what will be the reaction? AY into L, and on the other side FR into L by 2 minus into x bar dash minus x. Okay, so AY will be, obviously I can take either each of these force separately, or I can take only this resultant force. So in that case I will have only one force, because the resultant has already taken in the impact of all three forces together. So I will get this AY as 1 over L FR L by 2 minus x bar dash plus x. Okay, so I have this reaction AY in terms of FR and these distances L. So my major unknown is x, because I want to figure out this distance. So let's do another step. If I calculate the moment at this point B, or let me call this point as D. So if I calculate the moment at this point D, what will be the moment value? Sigma moment at point D is equal to 0. So I can call this moment as M2, and it will be equal to, and there are two forces on the left side of this point D. One is this AY and the other one is this F1. So I have to compute the moment of these two forces, and it will be the equal to the moment at point D. So the moment is M2 is equal to AY into L by 2 minus x.
Sir, M2 moment at B है.
Moment at point D here. So I have AY into this distance is, the moment arm of AY is L by 2 minus x, because this distance is x, the whole distance is L by 2, so this moment arm is L by 2 minus x, and the other force is this F1. So for F1 I will have minus F1 into D1. So this is the moment at point D, which is basically M2. So if I simplify this one, I have the value of AY from here. So M2 is equal to 1 over L. I will substitute the value of AY from this equation. 1 over L FR into L by 2 minus x bar dash plus x into L by 2 minus x minus F1 D1. So M2 will be FR by 2. If I multiply this whole term inside, so I will get FR by 2 minus FR x bar dash over L plus FR x over L into L by 2 minus x minus F1 D1. It will remain as it is. So again, if I simplify or multiply all these factors with this one, the final equation that I'm going to get is FR L by 4 minus FR x bar dash over 2 minus FR x square over L plus FR x into x bar dash over L minus F1 d. Now we have assumed previously that our maximum movement was existing at point under this force F2, and the value of that moment, let's say, was M2. So we know that if M2 is maximum, or if we want to maximize the value of M2, we have to take the differential of M2 with respect to the distance x and set it as equal to 0. Then we will, so basically we know that we have assumed that condition, and now we can apply that condition. We will take the differential of this equation with respect to x, then we are going to get the maximum value of the moment. So if I take the differential of this whole equation with respect to x, this will be 0, this will be 0, I will have this value, or I will have the differential of this equation, that will be minus 2fr over L, plus I will have the differential for this one, that is fr x bar dash over L, and this one will also be, or the differential of this one will also be 0. So now I can set this differential as 0. I will get minus 2 fr over L plus fr x bar dash over L. So if I simplify this one, I will get 2fr over L is equal to fr x bar dash over L. By the way, there is x with this term. So this will cancel out, this will also cancel out. So I will be left that this x is equal to x bar dash over 2. So what does this final form of the equation mean? That x is equal to x bar dash over 2. Let us see it. So this means that this x distance over here is equal to x bar dash over 2. What is x bar dash? X bar dash is the distance from the resultant force to the point, or to the point load, which we have assumed has a maximum bending moment under it. So this final form of the equation shows that if I have a set of moving load and I assume that maximum moment exists under one point or under a particular point, then if I should place that point load at a distance equal to x bar over 2 with respect to the center line, then I am going to get the maximum value of bending moment for that case. Okay, so now if I give you the simply supported beam, so now if I give you the simply supported beam and there are different set of there are different moving loads that are acting over this beam. So what should you do? You will figure out what is the center line of this simply supported beam, and you will calculate the resultant force, and you will place this moving load in such a way that the distance, or for example, let's say you assume that under this point load you have the maximum bending moment. So you will place this point load at distance half of this distance, half of the distance, or half of the distance of the resultant with respect to that point from the center line, and you will get the maximum, and you will simply compute the bending moment from the bending moment diagram, and that will be your maximum bending moment. But again, the thing is that there are three different loads in this case, for example, and you have to do this procedure at least 3 times to get the maximum value. For example, for now we have under this second point load or this point load, then it is quite possible that the maximum bending moment may exist under this point. So firstly, you will assume that it is under this one, and then you will assume that the maximum bending exists at this point, and now you will place this moving load or this load in such a way that it is at a distance half of the distance of the centroid with respect to the center line. Obviously, we are going to solve one example, then these things are clear. So still, if you have any question about this derivation, you can ask me now.
Sir,
Yes.
how we find the location of resultant force?
Location of resultant force. Let's say you have these three loads, 1, 2, and 3. So resultant force, obviously, you can find by simply adding these three. If this is 1, 2, 3, let's say, so it will be 3 plus 4, 2 plus 1, that will be 6. So the resultant force is 6, and you know these distances, these two distances, and you want to find the location of the resultant force with respect to obviously one of the force, one of the force. So you will take the bending moment with respect to this point 2, let's say. So sigma m2 will be 0. So if you take the bending moment, you will have this force 3 multiplied by this distance, if I call it as x1, and this distance as x2, and this distance as z. So you will take the bending moment, so that will be 1 multiplied by x2, or 3 multiplied by x1, and fr multiplied by plus fr multiplied by z. So you know this x1 and x2, and then you will get the distance of this resultant. And then you will take the half of this distance and place your point load at that distance from center line to get the maximum value. Did you get my point?
Yes, sir. Please.
Okay. So any other question about this one? If there is no question, then we can conclude this class over here. And in the next class, we will solve one example problem related to the simply spotted beam with different moving loads that are acting over it, and we will find out the maximum value of bending moment. And if you have any question, you can always reach me on Microsoft Teams. And by the way, I gave you one question in the last lecture. Has anyone thought about that one?
सर वो लोड से रिलेटेड था वो वाला क्वेश्चन, मतलब वो यूनिफॉर्मली स्प्रेडेड लोड था ना, वो फीट में था, तो उसकी वजह से फाइनल आंसर भी आपको फीट में ही होगा इसी वजह से, even though the beam is in meters.
But final answer should be in feet. But we were giving the final answer in terms of moment units. That was kip fit. So why were we doing that?
सर वो क्योंकि आपने जो लोड का शुरू में डिस्क्राइब किया था ना, वो आपने ख्याल से किप फीट में ही किया था, इसकी वजह से, मतलब सॉरी, जो आप किलोमीटर पर फीट था तो वो पर फीट के हिसाब से फिर इसकी वजह से ही आई थिंक कि फाइनल आंसर मोमेंट्स में जब डिस्क्राइब करेंगे, क्योंकि आपकी फोर्स फीट्स में है, तो आपका फाइनल आंसर भी फीट में होगा, नहीं सर?
Final answer is in feet, but our final answer was in kip fit. For example, let us open that lecture. So this was our beam. Yeah, this was our question. So in this question, you can see that I was multiplying the load with this bending moment component, which should be in kip fit, and the load is also in kip. So the final answer should be in kilo square fit, but we were giving this answer as kip fit. So again, just do it and think about it, and we will have this question in the next quiz.
Oh shit, yes sir.
So I hope you will have the answers by then.
Yes sir.
Excuse me sir, BSc के भी lectures YouTube पे upload कर दें playlist बना के.
These lectures are uploaded on YouTube already.
सर MOS के अपीयर हो रहे हैं लेकिन BSA के मुझे तो नहीं नजर आ रहे, या तो लिंक शेयर कर दें अगर है तो।
I have shared the link, but can anyone else confirm that they can see these lectures or not?
Yes sir.
Yes, sir, we can see.
Available है.
चलें ठीक है,
Yes.
मैं देख लूँगा।
Okay, but I will share the link again.
थैंक यू।
Okay. So if there isn't any questions, so we conclude this lecture over here, and at 12 we will have again the class of MOS to complete the example problem. So Allah Hafiz and take care for now.
Allah Hafiz.